Good afternoon, everyone. Today we are going to start a special type seminar topic Ramanujan and his contribution to number theory. Dear friends, all of you know that some are born talented, some work hard towards developing talent, while some spend their whole life searching for that one spark of fire which we all call passion. And then comes the rarest of the rare, known as God gifted or natural talent, who are born with special capabilities, perplexing brain power, and the ability to invent a solid foundation or any field of subject. Professor Suborno Issac Bari, 12 years old, the world famous little professor. His aims that spreading love among people and in trying to help the current generation of students understand the thrilling side in science and mathematics. He believes anybody can become an inventor or a discoverer. Professor Subarno Barik, now he is within us. On behalf of our college, at first, we convey our respect, love to Professor Subarno, and I would like to request Professor Subarno, please come on the dais with his father. Now, I would like to pray our Vice Principal Maharaj, most revered Srimad Swami Vedanuraganandaji. Please come, and I would like to request to felicitate to be Professor Subarno. Now, I would Subarno, please. Now, I would like to pray to our Vice Principal Maharaj to deliver his welcome address.
Revered Principal Maharaj, respected teachers, respected participants of this interactive session, dear students, and dear Subarno, who is there on the dais, and all our respected staff members. So, it is really a special program where we have a special child prodigy amongst us today, who will be interacting with you. So often, as Tuhin was telling, that often talent blooms at a different rate in case of different people. So that itself is a special phenomena, and we will really, we have many of us have seen Suvarno on the social media in YouTube channel and all, but it is really, we are really happy to have Suvarno and his father uh, amongst us today in this special afternoon. So, on behalf of Ramakrishna Mission Vivekananda Centenary College, Rahara, Kolkata, I extend heartfelt welcome to Mr. Suborno Issac Bari. So, he needs um, our Rana sir will give brief introduction about him, but apart from that, you can observe that he is a very focused person. So he is always doing some into some study. So I pray to the Almighty so that his talent blooms ever and ever, and he becomes a special asset to the mankind. And with these few words, we'll listen to him on his topic, Ramanujan and his contributions to number theory, organized by our college. And it will be really something special to remember forever. And so, all the best to Subarno for his future, and I welcome all of you to today's talk. So, with these few words, we are eager to hear to Subarno today. Thank you very much. Namaskars.
Now I would like to request to our most respected Dr. Prabhanjan Kumar Rana sir, Head of the Department of Mathematics, Ramakrishna Mission Vivekananda Centenary College, to give the brief introduction on Professor Suborno.
Respected Maharaj and other staff members and my dear students and speaker Suborno Bunik present in dais. Uh, Welcome all of you. Wish you a good afternoon. Now I introduce about Suborno Bari. Suborno Bari was born on 9th April 2012 in New York. He is 12 years old and he read in Malvern High School at 12th class. He is visiting graduate student at Stony Brook University. Recently, he has been accepted to New York University with a full scholarship and pursue a BS in MS Math and Physics. He is the youngest New York University student. Suborno is also a youngest qualifier for the examination AIME in US Math Olympiad. He achieved a perfect ACT math score 36 out of 36 and 790 out of 800 on SAT math and 5 out of 5 in AP calculus BC. At 10 years old, he scored 1500 in SAT and 34 in ACT. He has published two books, The Lab in the year 2019 and Manish 2021. Now I thank you all once again. Okay.
Thank you, sir, for your nice introduction on Suborno. Now we are very eager to hear Suborno. So I would like to request Mr. Suborno Barik to start his lecture. Please, Suborno. How does it work? Yes. Vikas sir, please come and. You can write here. can be projected.
With the pen?
Yes, you will see. এই লাইটটা কি অফ করে দেবে? You know how to write?
Okay, let me see.
Let me try. Let it try.
ওখানে দাঁড়িয়ে দাঁড়িয়ে লিখবে না
নাকি বসে লিখবে?
না না বসে না দাঁড়িয়ে দাঁড়িয়ে লিখতে পারো
So write it. Now ওইখানে লিখতে পারো.
প্র্যাকটিস প্র্যাকটিস
Yes, so that is correct. You don't look at this. Just you look this side.
I see.
এটা একটু বাড়িয়ে দিবি না ফুলটা, এটা একটুখানি ফুল স্ক্রিন না ওটা বলছি না, ব্রাইটনেসটা একটু বাড়িয়ে।
Okay, and if I want to erase, I just press.
Choose it. No, that is not.
Oh, you must click on it.
Yeah.
And then can
Yeah. Yes.
I can use the pen?
Yeah. You just choose eraser or pen, whatever you want.
by hand or by the pen?
By hand.
Practice.
And if you feel any problem, just call me. Yeah?
Okay.
Okay. You take it. So, is it okay?
Yeah. Namaskar. Firstly, before I begin my lecture,
Please start. Continue.
okay. Firstly, before I begin my lecture today, I would like to thank the honorable principal. Firstly, before I begin my lecture, I would like to thank the honorable principal Kamal Astanand for inviting me here today. I cannot express how excited I am to be giving a lecture at the Honorable Ramakrishna Mission Vivekananda Centenary College. I'm so excited to see all of you here today. But before we begin today's lecture, may we please rise for the national anthem? Thank you. Oh, please stop talking, by the way. Jana Gana Mana Adhinayaka Jaya He Vamatavagya Vidata Punjab Sindh Gujarat Amaratha Vavida Utkalavanga Vindhya Himachala Yamuna Ganga Uchala Jaladi Taringa Subena me jage Sab Shubha Ashish Mage Chahe Tab Jaya Gata Mangaladayak Jaya He Vatavaya Vidata Jaya He Jaya He Jaya He Jaya 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 He. Okay. Thank you, everybody. Okay, simmer down. As Swami Vivekananda once said, the powers of the mind are like the rays of the sun. They illuminate if you focus them. So please focus on today's lecture. If you have one, please take out your paper and pen. In fact, I have a spare notebook and pen right over there if anyone needs it. All right. Has everyone taken out their notebook yet? If they have one, of course. All right. So, once again, sisters and brothers of India, thank you so much for attending my lecture, and let's begin. Of course, if this works. Let's see. Oh. I might need to have some help again, perhaps. Oh, I see what I'm doing wrong, perhaps. Let's see.
Just
Can you move the window back?
yeah, just a minute. Nice. So
Okay.
say A plus B whole square equal like this, like this. So
Gotcha.
don't press here,
I see.
like this.
Okay.
Yeah.
If I want to change color, I
Yeah, just choose from this palette.
I see. I got it. Can you? Is there a way to raise brightness like this?
Whiteness,
A brightness.
brightness.
Yeah.
So,
On the screen like that. I see.
yeah.
Okay. Yeah.
Is it right?
That's good.
So see, this is the eraser and this is the pen, and this is the color palette, right?
I see.
Yeah.
Okay. That's good.
Don't press here.
Okay. So let me see if I want to pick this one.
Yeah.
Okay. So let's see.
Is it work?
All right. Let me just erase everything.
Yeah.
Okay. Let us begin.
Yeah.
Thank you. All right. So, with technical difficulties aside, today, this is the beginning of our lecture. Oh my God! Why can't I press the pen button? Okay, let's use the mouse, if I can. Okay, here we go. All right. So, let's get today's lecture started. So, let's begin first by talking about a few applications of number theory to get you hooked in. So it's a little bit hard to write like this instead of whiteboard, but I'll do my best. So, number theory. Okay. So, the biggest application of number theory is cybersecurity when it comes to computer science. So, if you want your data, like your pictures and your messages, encrypted, so that they are safe from anyone trying to eavesdrop or look at your conversation. So if you don't want anyone except the intended recipient to receive your picture, your text, your email, or anything else, cybersecurity will prevent that from happening. So this is through something known as PSA encryption, which is an algorithm that has to do with primes. Essentially, it takes a number known as a semi-prime. A semi-prime is a number that is the product of two prime numbers, or numbers that have no proper divisors other than 1 in itself. So like 7, for example, 1 divides 7, 7 divides 7, but 2 does not divide 7. Cannot. So, a semi-prime would be something like 77, which is 7 times 11. 7 and 11 are both primes, as you can see. So, these semi-primes are relatively easy to factor when they're only something small like 77, but when they get big, then they can be very hard to factor. For example, take this example. So let's see. What's something that I could think of off the top of my head? Alright, so for example, something like, okay. So, let's say you want to factor 979. Can anyone tell me the prime factors of that? No one, right? That's pretty good. Because 979 is only 3 digits. So really not that hard to factor. It's, as you can see, just the product of, I can't get my pen over here, 89 times 11. Alright. And 89 and 11 are both prime, by the way. The reason that we're picking exclusively semi-primes is because if you pick something that is more than a semi-prime, i.e. it has more than those 4 factors that you've given it, then it's very likely that you can just guess a random factor, or it's more likely that you can just guess a random factor and it will be true. We're trying to keep the amount of factors to a minimum. So then you might ask, well, why aren't we using primes? Well, here's the thing. Let's see. Can I scroll on this thing? Okay, let's see. I'm going to have to use my cursor here. So, we start by taking some prime, semi-prime, let's say 77, and then your intended recipient gets one of the prime factors. Now, computers have perfected the algorithm of division a long, long time ago. So it would take seconds for your computer to recognize, well, milliseconds for your computer to recognize 77 divided by 7 is 11. The other prime factor needed to decode your encryption. But let's say that you have neither of the two factors because you're a hacker trying to look at someone else's conversation. So you have neither of the two keys, and the only way that your computer knows to find these prime factors, there were slightly better algorithms, but this is usually how computers do it. It's just by dividing through manually. Does 77 divide 2? No. That gives you, what, 38.5? So that's out of the question. Does 77 divide 3? No. That's going to give you about 25.67. Does 77 divide 4? Well, let's think about it. No. 77 doesn't divide 4 either. 72 does divide 4, and 72 divided by 4 is, well, let's see here, 24 times 3, it's going to be 18. So we have 18.75 over here, at least I believe so. 77 is not divisible by 5 either. You only need to test prime for this case, however, so we can leave 4 out. 77 divided by 5, for example, would be 15.4. 77 divided by 7, aha, finally, we found the factor, 11. And then your computer can find the next factor from there. But that took much, much longer compared to the division algorithm. If we were doing that with the 979 thing, it would have taken almost forever. And that's a lucky case because it has a low prime factor, like 11. What happens when you have 2 prime factors that are both high on the list, like 113 and 89? Or even worse, you have something that's not just 3 puny digits, but let's see, almost 30, like this. How do I, okay. Something that has much more digits. Like, how would you factor something like this? It would be infeasible for a computer to just divide through over and over. But even for a colossal number like this, a human could still easily divide this by one of its prime factors, although it would probably take somewhere around 20 minutes. But it would take years to find the prime factors of this just by brute force, or Eratosthenes' sieve, or whatever other algorithm that we have that is optimized enough to find the prime factors of this function. So this is the biggest use of number theory, and that's why I find it the most important for keeping all of our personal data safe. So now, let's get into something that isn't just number theory, but appears in a variety of fields. But it's most useful in number theory, which is why this talk is titled Number Theory. All right. Here we go, and here we go. If you have ever taken calculus before, especially calculus 2, you might remember the notion of infinite series. So these are essentially series that either converge or diverge. What does this mean? Well, first we have to get acquainted with the use of what's known as a limit. I really wish I could open up other applications on here. In fact, GeoGebra is right there, but I suppose not. So let's get a red color for this one. So essentially, what is a limit? Well, let's say we have a function right over here. This is f of x, not meant to represent anything in particular. So let's say we have some point over here which corresponds to an x value of a. And let's say that f at that point is equal to some number L. Essentially, the limit as x approaches a of f of x. Let me just. Is there an undo button? Of course there is. Let's see. Wait, what? Oh boy. Oh boy, what am I doing? Can't. Okay. Let's see. Let's try undoing this again. Oh gosh. See, these are the benefits of a whiteboard. Don't get nasty pop-ups about entering latex text. No, I can just undo it manually. Okay, there we go. So, see, I have no idea how to use technology. All right. So the limit as x approaches a of f of x equals L if, and only if, we have some interval with length 2 delta, so ranging from a minus delta to a plus delta. Sorry for the bad handwriting here. Please pardon me. Such that for any range we have, let's see, for any range a minus delta to a plus delta, the values of f of a minus delta and a plus delta, not plus, comma, a plus delta, fall in between some L minus epsilon and L plus epsilon for all conceivable or all real. How do I get the pen to this corner? For all real delta and epsilon. This is just some fancy notation. It's for shorthand. You don't really need to worry about it. All right. So, this is the formal definition of a limit. You might think, well, why do we need it? Can't we see on the graph clearly f of a equals L? Why can't we just plug it in? Well, let's look at one graph where that's a problem. Like, which one? Okay. So I'm going to choose something like x plus 2 divided by what? Right. Okay. So let's just do something like x plus 2 divided by x plus 2 times x. Now, the thing is, for every other point, this looks like a normal graph of x because these two add up to the same number. So they just cancel out and you get x on the other side. But for x equals minus 2, it ends up being undefined because this will now give you the same number on top and bottom, but it's 0 over 0. We can't simply say that's 1. So it stays undefined here. So, however, we know that the limit as x approaches minus 2 of f of x is equal to minus 2 in that sense. So what does that mean here? Well, now we have to talk about limits approaching infinity. Essentially, what is a limit approaching infinity? So sometimes we have a function where we get closer and closer and closer to a certain value, but we never actually reach it. So these functions have a limit. or a horizontal asymptote. So the limit as x approaches infinity of this function is going to be some finite number. Now, for most functions, this isn't true. Like exponential functions, let's see, just regular polynomials, cosine and sine functions, which while they are bounded between -1 and 1, they don't have a limit at infinity. So for most functions, this doesn't work. But for a select few, this does. Let's see, can I add a page? I probably can, right? Oh, here it is. See? I'm a IT master. But, okay. Yeah, no. Okay. So, let's see. We did that. So now, let's talk about those actual infinite sums. Oh, I can write like this. That makes things so much easier. Scared that making contact would, make other marks. All right. So infinite sums have been long considered to be a paradox. So, for example, in the 3rd century, or around 200, there was a man named Zeno, I think he was Greek, who came up with Zeno's paradox. Essentially, you have Achilles here. He's a man from Greek mythology, and he is very good at running. So let's say he runs at 10 meters per second, which is pretty fast. And then you have a tortoise. Tortoises are not normally known for running. So this tortoise would go at, say, 1 meter per second, which is still extremely fast for a tortoise. That's like a normal human walking speed. So Achilles decides to challenge the turtle to a race. Since the turtle was already confident from winning against the hare, the tortoise agrees. But the tortoise says, since you are so fast, I must get a 10-meter head start. And so it was. So now the tortoise is 10 meters ahead of Achilles. So what happens? And we're not going to say the race is infinite. Let's say that the finish line is 100 meters away, all right? So who do you think is winning the race? Achilles, who moves at 10 meters per second, or the tortoise, who moves at 1 meters per second, but has a 10-meter head start? Who do you think wins? Well, of course, who is going faster here? Who is going faster, Achilles or the tortoise? Who is moving at a faster rate? Okay, so, yes, Achilles, the human, is moving at a much faster rate. Do you think the tortoise's head start will make Achilles unable to catch up? So who wins the race if the human moves 10 times faster, but the turtle has a 10-meter head start? Yes. Okay. So you might have reversed the paradox a little bit there, but here it is. So any reasonable person would assume that Achilles wins the race. And if you think about it, if you make a graph of their position function over time, so like this is position and this is time, if you make a graph of their position function over time, you will see this blue graph is going to be the tortoise. So he gets a 10-meter head start. So this would be x plus 10. And then this is Achilles. And this is just 10x. So it will take Achilles 10 seconds to complete the race. But it will take the tortoise because it moves at 1 meters per second, but only has 10, 100 minus 10 and 90 meters to cross. Or where is it? 90 seconds to complete the race. And you can see, obviously, that Achilles must catch up to the tortoise at some point. And Zeno saw this too. But here's what he thought. Well, to catch up with the tortoise, Achilles must first reach the point where the head start happened. But once he reaches that point, which is 10 meters away, so it takes him 1 second, the tortoise has already moved a meter in front of him. This is 11 meters and this is 10 meters. So the tortoise is already here. But then, once Achilles catches up with the tortoise's second position, he will find that in the 0.1 seconds that it took him to move there, the turtle has already moved 0.1 meters. So now this is 11.1 meters. And then, once he moves to that head start, the tortoise will move further, and then further, and then further. So Achilles will never catch up to the tortoise, right? Is that true? So who wins the race now? Achilles or the tortoise? Did you misread it? Achilles is the much faster one, but no. It's okay. All right. So, let's see if we can maneuver into making a new page. Aha, okay. So what's the resolution to this paradox? Well, Zeno thought it would take an infinite amount of time, across 10 plus 1 plus 0.1 plus 0.01 plus 0.001, etc. So he thought this sum equals infinity. So it would take an infinite amount of time for Achilles to catch up with the tortoise, or at least some amount of time that is larger than the time it takes for the tortoise to finish the race, 90 seconds. So Achilles must lose, right? Well, let's think about this sum. What is this? This is 11.11111, etc. Now, have any of you ever seen the decimal 0.111111, etc.? Any of you? Yes, 1 over 9. So, given that information, what should this be? You're moving the decimal place 2 spots to the right. So then what should this value be? Yes, that is correct. So, this is really not infinity. It's just 100 over 9. But how do we prove that? Well, let's think about this series. From now on, we're going to use these terms for a series. So let's say we're talking about the series of natural numbers 1, 2, 3, 4, 5, etc. Then 1 is going to be called A1, 2 is going to be called A2, 3 is going to be called A3, 4 is going to be called A4, 5 is going to be called A5, and I think you see the pattern here. So, if we wanted to make a general explicit expression for AK, what would it be in terms of K? Yes. Okay. So, now we're going to do a similar thing here by using exponents. So, you will notice that the first term, A1, is 10 to the power of 2. The second term is 10 to the power of 1. The third term, wait a second. Oh, whoops. This is 10 to the power of 1. This is 10 to the power of 0. This is 10 to the power of minus 1. This is 10 to the power of negative 2, so on and so forth. So, in terms of K, what is this sequence? Sorry? Yes. Now, of course, I don't want just one person answering these questions. The rest of you have to be more active. All right. So, yes, the answer is 10 to the 2 minus K. So how do we determine if a sequence does converge? That is, it has a finite limit at infinity, or the sum of all its terms over and over approaches some number that is less than infinity. Like in this case, where it approaches 100 over 9. How do we quantify that? Well, let's see. Let's figure out this page button. All right. So this is determined by this. The limit is or k approaches infinity of the ratio of a of k over a of k minus 1. So this must be equal to n, which is less than 1. Or we can just say this must be less than 1. And if you really want to be a pedant, you can say should probably also be greater than minus 1. All right, so let's test out the 10 to the 2 minus k sequence over here. So, what is a to the k for this sequence? Come on, it's right there on the board. Just say it out loud. What is 10 to the 2, what is a of k? Yes, it's 10 to the 2 minus k. So what is then a of k minus 1? It's not 10 to the... Yes, thank you. All right. So, then we get 10 to the 2 minus k over 10 to the 3 minus k is less than 1. Yes. So it should be pretty obvious that this converges. Now, let's talk about a series that seems like it should converge, but doesn't. 1 plus 1/2 plus 1/3 plus 1/4, etc. Now this is what is known as the harmonic series. So, as you can see, I don't think it's necessary to show you that a of k equals 1 over k. So then, testing it out on the formula, we get 1 over k over 1 over k minus 1, which is equal to k minus 1 over k. But that is equal to k over k minus 1 over k, which is equal to 1 minus 1 over k. Now, can anyone tell me what the limit of 1 over k is as k gets bigger? Yes. So you get 1 minus 0, so 1. 1 is not greater than 1, is it? So, that means that we cannot say the harmonic series converges. And in fact, it doesn't. If I remember correctly off the top of my head, it actually diverges and grows in a pattern similar to ln of x, or the natural logarithm of x. Let's add another page. All right, here we go. So now, let's talk about a more interesting series. So, you've already seen that 1 over k doesn't converge. What about 1 over k squared? By which I mean 1 over 1 plus 1 over 2 squared is 4, 1 over 3 squared is 9, 1 over 4 squared is 16, 1 over 5 squared is 25, etc. Do you think this converges? Aha, so most of you have taken calculus 2. Yes, by the p-series rule, this does converge. Oh, I suppose it would not p squared, but x to the p, right, where p is greater than 1. So, now, you might know that this series converges. Well, you should know that this series converges, but what does it converge to is the bigger question. Oh, yeah, okay, right. But do you know why? Or have you just seen it? Sorry? Okay, let's provide the proof of why it's pi squared over 6. So to do that, we're going to have to start from what's known as